one or two more topics on Scorep side in this session before, and you will have the chance to try out one of it, especially the energy counters part, before we would like to come to the review part and your experience and so forth. So yeah, these are really, I mark this one advanced topics, since they definitely don't apply to everybody, but since we have energy information available on CRAY, and I heard that there are people using OpenACC codes here, it might be worth covering those as well. Okay, so first thing is energy counters. On the PSPane system, energy information is available via this CRAY power monitor. You could say interface. It's not a performance tools interface per se. It's actually a couple of files in a SYS file system can be queried while an application is running, and gives you information about the power usage and the update frequency about this of this power usage. And for Scorep, there's a plugin. So Scorep also has a plugin system. There's a plugin library which can be used to monitor and record this power consumption and write it into the trace or profile. As I said, the power information is added to the trace counters and can then be analyzed using Vampir's counter display or performance radar, as with any other performance metric. This is like a test application, and I got the slides from a colleague of mine. So what this test application is doing is just generating some workloads where there's green, and it's idle when there's brown. And it has been used on a CRAY to just like see how accurate the information is and what problems there are. So the test pattern goes with decreasing intervals, and we have collected 3 counters here, or actually all of them are collected always if you enable the power plugin. First is the energy, measured in joule over time, and as the same energy counter increases over time. Second is the average power derived from this energy in watts, and it correlates fairly well with the test pattern. So if there is a load pattern here, we have a lot of power, and for a smaller load pattern, this power is also smaller. However, we see there are a couple of update issues, for example. So on the CRAY system, the power information is only updated I think with 10 hertz. Don't pin me on that. I remember it to be 10 hertz. So we won't see anything more detailed than that, for example. And there's also the problem that to find out if there's an update available, we have to query one counter, which is called the freshness counter. And if this one actually has increased, we got a new sample, and then we can query the sample counter, and then we have to check the freshness counter again to see that you're actually still in the same period of time of the last freshness counter. And so it's cannot be perfectly aligned with what the trace is showing us. Furthermore, the energy values are given by us by this CRAY file system or power interface, and they are digitally filtered. So in theory, there should be like a almost straight up here, then a plateau, and then almost straight down, but they go up every 10 hertz in some kind of filtered way, which is also an artifact of how it's measured. Another interesting thing is that we also get on a CRAY with accelerators, so CUDA cards attached, we get the power information for the accelerator separated from the power usage of the node. So in that case, it was the gromacs code has been used, which used MPI processes with OpenMP threads and one CUDA device on each MPI process, and in that case, one node and 4,000 iterations. So this time it's not the counter display, but what's called the performance radar. So we see the metric information for each node in that case, since we cannot get it for every process, right? And for every thread individually, we can only get it for the whole node or for the whole accelerator. usage here, and we have the accelerator power usage down here, and we both have the instant and average values. And yeah, if you look at this, you can see that, for example, for the accelerator, it's not the same everywhere, and it's increasing from green to yellowish here, and there are also a couple of hotspots, and it might be interesting to find out why that is. Why is this workload using a special or especially much power and energy in contrast to that other workload and so forth? And you could also compute from these two values, you could compute the only host side of power usage by just subtracting it. To do that, we can utilize another feature of Vampir, which is called customized metrics. So I think in almost every display which supports generic metrics like the performance radar or the counter data timeline, you can right click, and instead of selecting the metric, you can use customized metrics, which will give you a nice graphical interface to click together other metrics that are available, like counters, like function runtimes, and operations that are available, like add, multiply, log, and sinus, and so forth. And you can just connect them like in a data flow diagram to create a new metric. For example, you could create a metric that tells you the average, the function duration of each function type over time, or one that subtracts from the total instant power the accelerator's instant power. Another thing that you see here, if you look at the total energy that has been consumed over time in the total program run, you see it's pretty different for the different nodes. If your energy usage is one of your concerns in programming your application, then this is could be really interesting for you. So it might not be your concern right now if you're charged for hours. It will definitely be concern if you are the one who is giving you those hours, so if you are to maintain the machine. But it might change in the future that you're not charged for hours, but you actually charge for energy to consume, since it's the thing that the other guy has to pay for. Right? It doesn't pay you for time, it pays you for their electric bill. And in that regard, it's very interesting to see how much energy your code uses, if you're energy efficient or if it's just like wasting energy at some point. This is just a zoomed in version of what we have seen beforehand here, but this time a comparison of three different views of it. First is so it's the same trace, but in the first version it's all processes and threads. Here it's only the master process. It's only process 0 and only all threads and the accelerators or the accelerator of process 1, which are on different nodes. And so what do we see here? For example, we see there's also a different time span in CUDA, which might directly correlate to the energy consumed, since graphic cards are very energy efficient if you use them right, but they also consume a lot of energy if you don't give them enough of workload. So the idle power usage, for example, is also very high. So from an energy perspective, you always have to think, does my program properly fit on GPU, or am I wasting cycles there? Another thing that we see here, which is also an artifact of how it's measured, is that the accelerator, for example, is idle at this point in the program flow. There's no CUDA kernels running here, but this energy measurement for that is actually delayed. So first, the instant power seems to be updated by the CRAY system, and since this is 10 Hz here, you get it like one cycle after that, and the accelerator instant power seems to be updated even one update cycle later. So you always have to be a little bit careful of how precise the measurement you have done actually is. So the second topic I would like to cover here is OpenACC support. Who does know what OpenACC is? There are like 5 hands raising, one is raising 2 hands. So OpenACC is a directive or pragma-based model, pretty much like OpenMP in that regard, but it targets accelerators. And that's what the ACC stands for. And its most famous implementation by PGI targets NVIDIA GPUs as accelerators. So the PGI compiler will generate CUDA code for you, so you don't have to go through the tedious task of writing the CUDA API statement in memory management yourself, but you just, in the best case, write an Pragma OpenACC parallel loop around your for loop, and will do the rest of it for you. And so there will be native OpenACC support available in hopefully the next or the one after Scorep release. Sorry, but there's already some support in the 1.3 release. So since the PGI compiler is generating new source code with CUDA API statements and CUDA kernels from your original directive source code, it's effectively running CUDA as a backend. So we can already, using the CUDA adapter of Scorep, measure those compiler-generated kernels, and we can already capture those compiler-generated API calls. However, what we can't do right now is a direct measurement of the user-written directives. So you will get a kernel with a kind of generic name, and you will see all the CUDA API calls, but it won't tell you this correlates with the directive I have written in file X, line Z, something like that. However, in the upcoming release of Scorep, or in the future release of Scorep, we will be able to measure those OpenACC directives directly using a tools interface. So it will give you, like for OpenMP, it will give you a new function in your trace that does, this is my OpenACC parallel do directive, which allows us direct source code correlation. It's currently available as a Scorep prototype. I don't think it's like public prototype, but I'm pretty sure people can get this for testing, but it's not in a very stable state yet. So we are still to figure out how we want to have that look in the trace. And yeah, it's still currently under development. So if you're having a CUDA program right now, OpenACC program right now that generates CUDA code as a backend, you're free to instrument it with Scorep, and you're free to enable the CUDA adapter, which you might have to do manually by using --CUDA with Scorep, since you're not using the NVIDIA compiler, it cannot detect automatically if you're using CUDA. And it will visualize the internal, or let's say generated API calls and kernels, which looks pretty much like that. It's like a very simple stupid application, which has an OpenACC directive compiled with the PGI compiler, and this one generates a kernel called Core2.207 GPU and executes it on the default stream here, which might already give you a lot of important information if you know to which part of your OpenACC program that correlates. But the thing we want to go to, and how it is done in the prototype so far, is that we can use this direct OpenACC adapter to visualize those directives and generate kernels directly. So currently you will get, like, I have a OpenACC wait directive here in my source file swim.f with Fortran code at source line 232, and you can, for example, see the kernels has been generated. Yeah, we're not totally sure how to visualize that. So there is the option of showing the kernel directly, the CUDA kernel. There's also the option of showing more or less this for the time this kernel could run on the on the device, to show like a generic function that corresponds to this directive on the device, which does not necessarily be the kernel, but it's just, okay, it's not a launch, but it's a wait, it's the synchronization. So the kernel could run from that to that point of time, which would then be more directly be correlatable to your actual source code. However, it doesn't give you the precise backend information. On the other hand, if you would use another backend instead of NVIDIA for OpenACC, you wouldn't be able to get this through the CAPI actually is. One probably one remark if you want to try that yourself with OpenACC. So currently there is an issue with the CUDA headers and the PTI compiler. So it will only work if your PTI compiler, I think, is 14.7 on your, and you're gonna need some kind of fixed CUDA headers that can work with that compiler to build Scorep. For OpenACC itself, it's totally fine. And I think on a Dane system it has been configured correctly, but if you're planning on installing Scorep yourself somewhere, keep that in mind and ask us about it if you are unsure where to go. So I definitely haven't tested with the CRAY compiler, and I'm pretty sure that my colleague who implemented that hasn't tested with the CRAY compiler either. So I cannot tell you actually if it will work or not. Theoretically, it should work. To at least for this way of things, to the rest with the CUDA adapter. Okay, so Jean-Guillaume prepared. It was so nice to prepare the Jacobi example for us, and it should be in home or in Scratch. Okay, so the source code can be copied from this location. Users course 01 JG and then Jacobi CUDA CSCS. All right. Yeah, exactly. So there's one step that's different now, that in the make process we have to use dynamic linking here. So Scorep has been built with static libraries only, so it can use link them in statically by default. But for the plugin to work, since it uses DL open and so forth during runtime, we have to do dynamic linking, which would be enabled by default if we would use shared libraries of Scorep, but since that's not the case, we have to use that explicitly. So you should be able to just like load the environment and then do this make call. You can definitely try it on your own application. I mean, it's easier like to have it tried out on a very simple example beforehand, since your application is probably like 100 files or something. Okay, and did you update all of the batch files or just the tracing? Okay, and let's have a look in the run Jacobi underscore tracing. Okay, so what has been done here? I mean, from the general configuration, it's totally the same, but we're telling Scorep to use metric plugins, in particular the power monitor plugin that has been created, and we're also telling it that for this power monitor plugin, we want to collect all counters, which is the only way to go right now for that particular plugin. One thing we might want to update is fix the issue with the OpenMP num-thread. So using actually CPU per task equals 3 in that case, leaving that at 2 and using 3 down here. So we don't have the problem that our CUDA thread, background thread, interfering with the OpenMP part. Okay, that should be it. Didn't complain so far, so we can have a look at the trace that has been generated. And you can open, for example, the performance radar now. Yeah, this one. Right. So we have, for example, the energy metric over time. And let's just open another instance of the performance radar. And we can select a different metric here. So for example, we can go with the accelerator energy over time. Yeah, that one. And yeah, we could also look at, so the energy is, of course, constantly increasing, sometimes more or less. We could also look at the power usage, which is more like an instantaneous value, or the instantaneous value computed from that. So if you go to another time to set metric, for example, have a look at the power or the accelerator power, which is the power usage at every given point of time. And as expected, the power usage gets a lot higher when the accelerator is actually used for doing something, which makes sense. And maybe we can like filter out this initialization part by modifying the scale down here. So if you can like increase the lower part of the scale into the, I don't know, the 60s, something like that, we see how the power differs across time and over the nodes. So apparently this node, or this accelerator, seems to consume a lot more power than that one. Might be interesting to find out why that is. But we will also try to zoom in a little in time, so we can differentiate the OpenMP and the CUDA compute section, and see if they are long enough that we get different measurements. But so obviously those compute sections, I mean, it's like only in the tens of milliseconds, so they are too short that this counter for this counter to be updated. The granularity of this counter is too large for like very small iterations. Could you right click in any of the metric displays again? The top, yeah. What other metrics are there available for energy? Right, so there's also the power usage of the host, or there's a freshness counter, which means how often this is updated. And it seems it's not updated at all in here, but if you zoom out in time again, yeah, I mean, it gets updated increasingly, so with every update it adds 1 to this freshness counter, but it only gets updated about 60 times throughout the application, which makes sense since it's sampling the energy with 10 Hertz. So we would need a lot more of computation on top here to actually see differences between the phases. And maybe if you can right click in one of the counter displays once more, there's this customized metrics option. You go there, and here you see all the metrics that are available so far. And if you click at add on the top right corner here, you can like click together your own metrics. So for example, here there has been choosing a metric from the group of trace counters. You could also choose from the group of function durations or function counts, but you might want to go with trace counter at this point. And then see which trace counters are available. For example, energy, accelerator power, and so forth. And we can say if we want to use the absolute readings or interpolated readings, or the number of times this counter is incremental. And if you would click on any of the right area here, right click, you can add another metric and you can add another operation. Drag around those windows as you like. For example, you could use power, the node energy, that one, and then right click in the right area again, add operation. Oh, sorry, not another metric, which would be subtract. and then we could subtract from the total energy the accelerator energy, for example, which would give us at least a fair estimate of what the rest is doing. And then it's like a nice, what's it called? Yeah, the name of the tool. And then we could give a name to the metric, like energy host or something like that. See, acknowledge that. We have a new metric down here. Acknowledge the second time. And then we could have a look at this metric, for example, yeah, exactly, in the top metric. I think it's the last one. Yeah. So you can like customize your metrics and do any operation that has been provided here. So the energy, it's accumulated over time. So it's always consuming more and more energy over time. It would be like counterintuitive if it go like any other way, right? But the power, we have only energy here. If you can change any of these to power again, in contrast to energy, the power is like the instantaneous power over which energy. So collecting those energy counters will only work in tracing mode and not in the profiling mode of CRAY, since they cannot be collected per individual thread, but only per node. And apparently this is not supported in profiling.